Okay, chapter 19 is on vibrations and waves. So a vibration means something's moving back and forth periodically about an equilibrium position. And when many particles are vibrating and kind of connected to one another, you can get a wave which moves energy through space, like water waves or light waves or sound waves. And so here, for example, is a model of a bunch of particles that are making up what looks like a water wave. And so the individual particles, if you look at any one of them, they're all just wiggling back and forth. They're vibrating around an equilibrium position. But you can also see the wave crests actually moving along and carrying energy with them. So a pendulum is something that vibrates, and the period is defined as the time it takes for a pendulum to swing back and forth one time. And for a pendulum, the longer the length of the pendulum, the longer the period. So this mass on a string has a short period. This mass on a longer string has a longer period. A sine curve is one way of visualizing a wave. So for example, if you have a pendulum that has a little bag of sand on the bottom with a hole that lets the sand fall out, and you have a piece of paper dragged underneath it, this pendulum will trace out a sine wave as it swings back and forth. A sine wave has an amplitude, which means how wiggly it is. So the amplitude is defined as the distance from the midpoint out to either a crest or a trough. These are the crests, these are the troughs. And the wavelength is the distance between adjacent crests or adjacent troughs. Frequency is how frequently a vibration occurs. It has unit hertz, and some examples are pendula have 1 hertz, one vibration per second, or maybe less than that, or slightly more. Sound has frequencies of hundreds or thousands of hertz. Radio waves can have millions of hertz frequencies, and cell phones operate at the billions of hertz or gigahertz. And period and frequency are related by the equation period equals 1 over the frequency. Period in seconds, frequency in hertz. Or frequency is 1 over the period. So again, frequency in hertz, period in seconds. So in these curves, if you have a long period like this black oscillator, then that is a low frequency oscillation. If you have this blue oscillator, the period is a little shorter, quite a lot shorter, and the frequency is much higher. Wave speed describes how fast the crests or the troughs move through a medium. So it's the speed of the disturbance. And that is related to the frequency and wavelength. Wave speed is the frequency times the wavelength. For example, here are waves where the wavelength is 1 meter. This bird standing here sees the water going up and down with a frequency of 1 hertz. So 1 hertz times 1 meter equals 1 meter per second. There's 2 kinds of waves, transverse waves and longitudinal. In the transverse wave, the direction of vibration is perpendicular to the direction that energy travels. This is characterized by sort of a side-to-side movement, and examples would be a vibration in a string or electromagnetic waves, such as light and radio. The electric field oscillates perpendicular to the direction that the light moves. In a longitudinal wave, the direction of the oscillation is parallel to the direction that the energy travels. It's like a backward and forward movement, and it sets up compressions and rarefactions. And the best example of this is a sound wave. So here's a sound wave. There's a speaker off to the left. This is shown in very, very slow motion. And as this speaker oscillates back and forth, when it pushes to the right, it creates a compression region, and that compression region travels away from the speaker at the speed of sound. And as the speaker oscillates, there's multiple compression regions separated by rarefaction regions, where the density is a little lower. And so in this compression region, the density is a little higher. Also, the pressure of the air is a little higher, which is why sound is sometimes called a pressure wave. But again, if you look at this little red, we've colored this molecule of air red. Look at any molecule, all the molecules are just vibrating back and forth, while the wave carries energy from place to place. Interference occurs when two or more waves exist at the same place, and the superposition principle is just the disturbance of one wave plus the disturbance of the other wave equals the disturbance of the resulting wave. So when two sine waves are traveling along in the same place and their crests match up with their crests and the troughs match up with the troughs, this can create a wave which has a greater amplitude than either of the original waves, and that is called constructive interference. However, if two sine waves are added up and the crests of one wave match troughs from the other, or troughs from one match the crests from the other, then the resulting wave can have a lower amplitude. And in fact, if they can even cancel out so that there's no sound at all. This is destructive interference. So standing waves are a result of interference, where you shake one end of a rope and there's a fixed wall which reflects a wave, and what happens is the incident wave interferes with the reflective wave and sets up the standing wave. Standing waves are characterized by nodes and antinodes. A node is a region where the disturbance is always zero. So here are two waves. The red wave is traveling from left to right. The green wave is traveling from right to left. And their superposition, or their final wave, is this blue wave going up and down. And you can see this is a node where there's never any vibration. The sound is quiet there. And antinodes are in between adjacent nodes, and that's where you have maximum disturbance. How you make a standing wave? Well, you just have to tie one end of the string and shake the other end, and this will create like a big standing wave. If you shake that string with twice the frequency, you'll create another standing wave that has a node in the middle and two antinodes. If you shake the string with 3 times the original frequency, then you can set up another standing wave that has 2 nodes and 3 antinodes. And in fact, standing waves is how all musical instruments work. Any stringed instrument is setting up standing waves in a string, like a guitar. And any wind instrument is actually setting up standing sound waves in a tube of air. The Doppler effect. So if there's a source of sound which is not moving, and you listen to it, you hear the frequency that it is emitting, called the rest frequency. If the source is moving, you might hear a different frequency. For example, if it's moving towards you, you will hear a frequency that's higher than the rest frequency. And if the source is moving away from you, you will hear a frequency that is lower than the rest frequency. And then if you measure the difference between the frequency you hear and the frequency that you know was emitted, this rest frequency, you can actually measure the speed of the source. And this is how these Doppler guns work when a police officer measures the speed of your car. It's sending out waves which are reflected off your car, and he knows what the frequency of the wave, the original frequency of the waves is, and he can measure the frequency of the waves that are reflected off your car, and from that difference in frequency, he can measure what your speed is and give you a ticket. And the Doppler effect geometrically is quite simple. The police car is moving from left to right here, and so if you look at these crests or wave fronts, they'll be bunched up in the direction that the police car is traveling and stretched out behind the car. So this wavelength is longer behind the car, and longer wavelength corresponds to lower frequency. So if the siren's rest frequency sounds like wee, then this girl will hear a wee. But this boy in front, the the waves are all bunched up here, so you have lower, shorter wavelength, which corresponds to higher frequency. And so instead of hearing wee, you'll hear a wee sound.